Okay, so hello and welcome to our seminar today. It's my pleasure to introduce Filippo Bonchi, who will talk about logic of hypergraphs today. Just a bit of his background in case you're not familiar with him. So he's been working for a long time at the interface of category theory and concurrency theory, not strictly in graph transformation, but always very close to it. And he's essentially from the same family in Pisa that many of our good friends are from as well. So it's sort of by inclusion in the community, he's certainly one of us. And he's been interested recently in graphical models, in particular in the context of string diagrams and other things that we also heard about in this seminar already. So I'm looking forward to his thoughts on these things. So please, Filippo.
Okay, thanks a lot, Raiko. Thanks to everybody to be here. So indeed, in the last year, I've been working a bit on string diagram and their relationship to graphs and graph transformation. And let's say the very first work of this line of research was this paper together with Fabio Gadducci, Alex Kissinger, Paweł Sobocinski, and Fabio Zanasi, which is rewriting modulo symmetric monadal structure that I think Pavel already showed in this line of GReTA seminar. What I'm going to show you today is this paper that I've done with Jan Sieber and Paweł Sobocinski, which is called Graphical Conjunctive Queries, and which inspired several other work, like this one with Dusko, Pavlovic, and Pavel, functorial semantics for relational theories, and a more recent one submitted, which is about Cartesian bicategory and hyperdoctrine. And also the PhD thesis of Jan Sieber is based on the idea of the talk that I'm going to show you. So given the opportunity of speaking for 1 hour and also having the opportunity of recording, I've been thinking I've decided to give a, how to say, not to go to give an overview and to go in breadth, but rather to go in depth and really go through the proof of the main results in here, because in my opinion it is a very informative proof. It's also easy enough to be shown in 1 hour. At least this is what I hope. So I'm going through the several steps of this proof, and each of these steps I think it's quite interesting on its own. Before proceeding, you see that I've changed the title to the talk. I mean, it's a different kind of title, and maybe the reason will be clear at the end of the talk. But for the time being, I want to say that I'm not going to talk about a logic for expressing properties of hypergraph or hypergraph transformation. I'm rather talking about a logic which is underlined by hypergraph, in the sense that hypergraph work as syntax for this logic, and hypergraph homomorphism are exactly proof. So it's like some sort of deep structural logic encoded into hypergraph. I think it's extremely interesting and can really inspire lots of application and future works, a clear understanding of this underlying logic. So our starting point is a result by Chandra and Merlin in 1977. It was to solve the problem of query inclusion. So this is a problem from the theory of database. So conjunctive queries, these are those queries which in SQL are called select from where, are just formula of the regular fragment of the first order logic. So this formula phi, can be either true, or the conjunction of two formula, or the equality of two variables, in this case xi and xj, or the existential quantification of a formula, or some symbol r applied to some to some variable. Here I have to say that these symbol are taken from some signature sigma. So this is just a set of symbol equipped with an arity. And then a database is a model. So what is a model? This is just a set X together with an interpretation for each symbol in R is interpreted as a relation. So a relation R with arity N is a subset of X up to the N. Okay, and then one can, given a query or a formula phi and a model M, one can just evaluate the formula in the model in the obvious way, as we usually do with the first order logic. Just to be sure we are on the same, we are understanding each other. Let's see an extremely simple example. I have this formula that exists Z0 such that x0 is equal to x1 and R of x0 z0, and I want to evaluate this in some model M. So let's say we have a set X which only contains A, B, and C, and there's a relation R. So R is a binary relation in this case. We have this only contains A, B, and BC. Then the evaluation of phi into M is just the assignment of the free variable of the formula phi to the element of X. So are those assignments which make the formula true. So in this case, I can have either this should hold. So x0 should be either A or B, and then we know that x0 is equal to x1. So the possible the possible assignment here are just either x0 goes to A and x1 goes to A, and x0 goes to B and x1 goes to B. Is this clear, or are any doubt on this? I'm trying to really to explain all in details and avoid any misunderstanding. So if something is not clear, please ask me now. Okay, I guess it's clear. So now the problem is we say that two formula phi and psi, or two queries, are equivalent if and only if they are equivalent in all the possible models. So it tells that for all model M, if I evaluate phi with and I evaluate psi in M, so they are equal. They denote the same set, and the inclusion is the same. I'm asking for inclusion. Okay, this is the kind of problem that this is the problem of query inclusion. It's the kind of problem that Chandra and Merlin faced. And they also provide a solution, which has a lot to do with hypergraph. So the solution that they found, say, translate every formula phi into an hypergraph, which we call G of phi, and then they prove a theorem. So if this translation is made in a proper way, they prove a theorem which say that the query phi is included into psi, which means that for all possible model, the interpretation of phi in that model is included into the interpretation of psi in that model. So this holds if and only if there exists a graph homomorphism on the other way around. So which go from G of psi to G of phi. So let's see, and I don't want to give you how this translation works, because we'll see this later in a more detailed fashion. But just to give you an intuition, it's rather easy. Let's start with this formula psi. So this formula psi, I say there exists z0, z1, such that r of x0, z0, and r of x1, z0, and r of x0, z1, and r of x1, z0. So the idea is that nodes are represent variable. So here I have variable for x0 and variable for z0, and the hyperedge represents the relational symbol. So here I have just r, and then so this one represents this bit, and then I have r1 x1 z0. So I have here x1 and r, which go to z0, so the same z0, and then I have z0 z1. So here we have some z1, and I have to add one hyperedge this, and then I have finally I have x1 z1, which is this. Okay, and then to represent the existential quantification, so I have to distinguish between bound and free variable, but it's rather simple. The idea is that free variables stand in some sort of interface, and this sort of graph of interface are kind of familiar in the graph of in the community of graph transformation, and they are known as cospan of hypergraph. And okay, in this case, the interface is just telling me that x0, I have x0 and x1, which are the free variable, the formula, and this point exactly to this gadget here. Okay, and the idea is that one doesn't want to know how the variable are called, so all these are removed. So this hypergraph, this is an hypergraph, and this is an hypergraph with interface. All these represent this kind of formula, represent the formula phi. So let's say this is G of C. While G of phi, so this is quite simple. Here I have R, here I have Z0, here I have X0, and I have that X0 is equal to X1. So in my interface, I have two free variables, X0 and X1, and they both point to the same node. So this is another hypergraph with interface. Okay, and the fact that this query is included into this query can be just proved by exhibiting an homomorphism of hypergraph. So the idea is that this homomorphism of hypergraph has somehow to respect also the interface. So basically, we are forced to map x0 and x1 in here. Okay, and then the nodes which were representing z0 and z1 are mapped into this node here. And then all the hyperedge are mapped in the obvious way, in the only hyperedge of I forgot to mention, this is G of phi. Okay, so this is known since 77. We are going to try to give a deeper understanding of this, and to make it a bit more algebraic. So what we discover is this love triangle. So we have this result by Chandra and Merlin, which relate logical structure, so the calculus of conjunctive query, with combinatorial structure, so this hypergraph with interface. What we show is that there are two more sides, and this form a triangle, which are related to category theory, and in particular we have some categorical structure which are free Cartesian bicategories. I will show. I will use this slide through the talk several times. The point is that to begin with, we somehow we get rid of queries or of first order formula by using these graphical conjunctive queries. So basically, we will use these, and these replace. I mean, the fact that these two different calculus, the graphical one and the conjunctive query, are equivalent is rather straightforward. So let me start with these graphical conjunctive queries. Are there any questions so far, or you want to ask me something? Something is not clear. Okay. So if I don't hear anything, I'm not checking the chat. So
I'm going to. Sorry, Filippo. I'm monitoring the chat, and I'm going to let you know if there is a question that is, I mean, not for discussion, but really needed to understand the following proceedings.
Okay.
Yeah.
Okay. So the graphical conjunctive query is a calculus of string diagrams, a very basic one. So basically, our term are circuits which have some ports on the left and some ports on the right, and these circuits can be composed in parallel like this, or in sequence. The composition in sequence can be done only when the right port of the leftmost circuits are equal in number to the left port of the rightmost circuits. So using these two basic operations, which are just composition of category and monoidal product, we have several basic circuits. So we have the usual discharger. The intuition is that these receive any possible signal on its only leftmost port and produce, and there's no rightmost port, so it produces nothing. The copier receive one channel in the leftmost port, one signal in the leftmost port, and duplicate the signal in its two rightmost port. And these are the same behavior, but mirrored at the how to say, swapped of 180 degrees. Then we have a circuit for the empty circuits, the single wire which represent the identity, the twist which allow us to cross wires, so these are symmetries. And then at the end we have some boxes which are labeled with some symbol, which are again taken from a signature. So here we have a signature sigma. So we have that R belongs to sigma, and sigma is a monoidal signature in the sense that to every symbol in sigma, for every symbol in sigma, we have both an arity and a quality. Okay. Then the semantics is defined as for formula of the regular fragment. So we need a model. Is defined with respect to a model, and the model is just again a set X, and for all symbol in the signature with arity n and coarity m, a relation from X up to the n to X up to the m. And these give you all these rules give you the semantics as one would expect. So see that for the sequential composition and the monoidal product, we just use here composition of relation, and this is just a Cartesian product of sets and relation. You can see, for instance, the discharger receive any possible signal X in the big set X of our model and produce nothing. So this bullet here is just to mean that this is the only element of the set. So you have that bullet is the only element of the set 1, which we use for X up to the 0. And okay, for sure, to translate the relation symbol, we need how it is defined by the model. Okay, let's see some example, and let's see how this work. Just to get a bit more confident with this calculus, with this semantics, which is really the main part. Once we have understood this, all the rest is rather will come quite naturally. So let's say I want to have this model here, and I want to compute the semantics of these circuits with respect to this model. Then I have only what should I do? I know that R can be either AB or BC. So I basically can put here AB, and then in this case I will have A. So because these circuits force me all the value to be the same, and so this is okay. Otherwise I can have B, C. I have B and B again. So the semantics of this formula will be the vector will set AA with some bullet to say that I have no ports on the right side, or the pair which contains the vector BB. So these are the only two possible outcome of evaluating the query on this model, on this database. Let's consider now this second bigger one. You see, this resemble a bit the graph the hypergraph with interface that we have considered. So here, so let's say I give to the first R, I give value AB. Then here I have A, B, and then so all this black structure basically is forcing me to give the same value B here, and the A structure is telling me this should be A and this should be A. So since R with A can only go to B, according to this, I should also have B here, and the B here is going all around here. So here I have a B as well, and here I can only have an A here, here, and here. So AA is for sure a solution, and I can also do BB, as you can expect. So if I put B and C, then again here I have C, then here I have B, B, C, C, B, B, and B. So, okay. So you see in this case, so can I now, for instance, try to have here to put here this other pair BC? I cannot really, because I cannot have a C here. So in this particular model, the two are equal. Okay, but let's try to think to another model. So let's take a model M prime. Where R is actually mapping. So I change B. I change BC, and this becomes BB. Okay. Then now I can also have other. I can also have other. I can also have other values. I can have, for instance, AB. I can have here A, B, here I have A, B. But now to this B and to this B, it can correspond. Okay, A again, but it also can correspond B because of this. So I can put here B, B, and B. So I can get AB, which is not in this. Here the A and B should always be equal. So somehow this was to show you that for every possible model M, this inclusion holds. I mean, it's not a formal proof, but I hope I gave you an intuition of how one have to reason about these things. And indeed, you can also think to this formula as, let me write it in yellow. So to this formula, this can be thought as the formula. There exists Z0 such that x0 is equal to x1 and R of x0 Z0. And well, this is the other formula that we considered before. So there exists Z0, Z1 such that R of x0, Z0, and blah, blah, blah. I mean, you know what I mean. Okay, now I want to show you something else. So let's consider this simple gadget here. I want to compute its semantics with respect to this M. So what is this saying? So this is equal to the semantics of these composed, I mean, the composition is relational with the semantics of this. So this is just equal to the set of all x which belong to my x. So this is just equal to, to A bullet, B bullet, and C bullet. Sorry, I did it. I missed up the type. So this one is the semantic of this in M, and this one bullet A, bullet B, bullet C is the semantics of this one. So I have to compose the two, and when I compose the two, what I get is obviously the relation which only contains bullet bullet, which is exactly the semantics of the empty circuits. So bullet bullet is the semantics of the empty circuits. This is by definition. So because the empty circuits is the identity over 0, and the identity over from x0 to x0 is the relation which contains bullet bullet. Okay, but now imagine that we consider another model M, which has no element, which is empty, where x is empty. So in this case, when I compose these two, if x is empty, here I would have basically two empty relation. So we'll have empty relation composed with empty relation, and this will be the empty relation. So intuitively, you can think to this as to the formula there exists x such that true, and this one to the formula true. And we will see that graphically these are two very different things, and indeed they're not equal. They only coincide when the domain is non-empty. But in general, one has an inclusion, so one usually has that this is included into this. Okay, very nice things of the of graphical conjunctive query is that we have a simple set of axioms which allow to reason about these formulas, and moreover, this set of axioms, as we will see, is sound and complete. So the axioms are so you see here a first set of axioms which is saying that the copier and the discharger form a commutative comonoid. So this first axiom is basically saying that if you first copy and then you discharge is equal to do nothing. If you copy and then you swap the two copies, this is just equal to just copying. Or if you copy and then you copy again the first copy, this is equal to copying and then copying the second copy. So this is associativity, commutativity, and unit. Same things happen for their mirror image. So their mirror image form a commutative monoid. And the monoid and comonoid together form a special Frobenius bimonoid. So this is the usual S equal to X equal to Z formula, the Frobenius equation. And this is the special equation. And then we have some inequalities, which we will see play a very different role, but they're very important. So the first one, the first group of inequation is telling us that the discharger is left adjoint. So we have the unit. So this is the unit. So we have that the identity is more or equal than this. And if you think in relational terms, this is the identity relation, and this is the total relation. So it's rather obvious. And this is what I've just shown you. That there exists X true, smaller or equal than true. Then we have that the copier is left adjoint, and again this is the unit, and this is the co-unit. Also, if you think these are rather intuitive. Basically, this is imposing a constraint which say all the signal here have to be equal, and this is posing the constraint saying that here and here should be equal, and here should be equal. So this is clearly an inclusion. This is constraining much more than this. And then we have that all the relation symbol R form a lax comonoid homomorphism. So that these two inequalities holds. Okay, some of you that are familiar with the Fox theorem for Cartesian category, they know that Cartesian category are seen as symmetric monoidal category, where every object is equipped with a commutative comonoid, and every arrow is a comonoid homomorphism. So this is equal. For relational reasoning, we need this smaller equal, and this is indeed all what we need. Okay, and then let me say we define an inclusion, which I write it like this with the smaller or equal on CB sigma in the obvious way. I mean, considering each of the equality as an inequality, and then taking the reflexive and transitive closure. And then one define CBC, the quality, CB sigma, by in the obvious way. I mean, intersecting smaller or equal with its op. This distinction will be kind of important later on, but for the time being, we define them like this. Okay, and then once we have this definition, we can use them to prove inclusion amongst formula. So here I show you. So this is the first term, and we show that this is greater than this one. This is basically what I've shown you before, like reasoning, and this is a proper proof. So first of all, we move this to R. We can, because of the lax comonoid morphism, we can move this two out of here. Since it's lax, we need the greater or equal. So from this we get this, and similarly here. Now for this equality, you see we are basically transforming this into this, and this all because of what is called spider lemma, which always solved in Frobenius algebra. So now we are with this, and here we can just use the fact that the discharger is the unit of the copier. So we get rid of this, and we transform this into an identity. And now here we are using the adjointness. So here we have the identity over 2, and we can replace it by this one because of this axiom. And again, we can use the lax comonoid morphism property. So these go here. And now separability, which allow us to transform this into the identity. Okay, and the point is, can we prove any possible inclusion through this axiom in this way? And the answer is yes. And this is our theorem 1. It tells that the inclusion with CB sigma holds. So if and only if for all possible model, the interpretation of C in the model is included into the interpretation of D in the model. Okay, I'm going to prove theorem 1 at the end of the talk. This is the main theorem that we are going to prove. But first, I want to tell you what are those axioms. Those axioms are exactly the axiom of Cartesian bicategories. So a Cartesian bicategory is defined as a symmetric monoidal category enriched over posets, such that every object X is equipped with a special Frobenius bimonoid. So this basically means that all these axioms holds, and then that we require that the monoid and the comonoid are adjoint, and that the two inequality on the left and in the center, and finally that every arrow is a lax comonoid morphism. These are exactly all the axioms that we have seen. And as expected, a morphism of Cartesian bicategory is just a functor which preserves the monoidal structure, the poset, and the monoid and comonoid. Okay, so the first example of Cartesian bicategory, the archetypical example, is the category rel of rel and relation. The monoidal product is the Cartesian product, and its unit is just the singleton set 1, which we represent with the set which only contains the bullet. And then it's interesting also to consider the Cartesian bicategory freely generated by sigma, which we denote as CB sigma. Well, this is rather simple now that we know. This is the symmetric monoidal category, which has as monoid of object the monoid of a natural number with addition and 0, and arrows from n to m are circuits of the calculus of graphical conjunctive queries, having n ports on the left and n ports on the right. And the circuits have to be quotiented by the equivalence relation that I have just introduced, and are ordered by the ordering that I've just introduced. And now I have a question for you. Please answer, even if you are muted. I cannot see the chat. So maybe Rako, tell me. So what is a morphism? I want to leave you some minutes to think about. What is a morphism of Cartesian bicategory from CB sigma to REL? I mean, those of you which are familiar with Lovier theory and functorial semantics should be able to guess. Can I see the chat? No.
I'll let you know if there are any replies. A model?
Yes.
That was Andrea, not me.
Yes. Bravo, Andrea. It's a model. Why it's a model? So what basically a morphism is has to preserve basically everything. So we have very few degree of freedom in our choice. So we have to choose where we map one, the object one. So in one we map to x, and then 2, which is equal to 1 plus 1, has to be mapped to x monodal product x, which is just equal to x squared, and any n has to be mapped to xn. And then the other degree of freedom is for the relational symbol r, which is mapped in whatever relation rho of r from xn to xn. So a model is really given just by a set. So I mean, a morphism is just given by a set x and an interpretation for each relational symbol. Okay, I hope this makes sense to you. Okay, we have now theorem. So we have now shown these sides of the triangle. So the theorem 1, which relate free Cartesian bicategory and GCQ. Now I want to show you hypergraph with interface. I realize now that only 20 minutes are missing. So okay, let's say, so first of all, we have to fix some signature sigma. And again, this is a monodal signature. Let's say here we have R and S, and the arity of R is 1, the coarity of R is 2, and the arity of S is 2, and the coarity of S is 1. So this is an example of an hypergraphical interface, as you expect. I'm sorry for this here. This is an hypergraph in the usual sense. So we have nodes or vertex and hyperedge, and here we have the interface, which points to some of the nodes of the hypergraph. And formally, these are cospans of hypergraph, but the interface hypergraph and the two interface hypergraph are discrete in the sense that they have no edge, and thus we can represent them by natural number n and m. So these are taken somehow ordered as well. And this is something very well known in the graph transformation community. So this hypergraph interface
I cannot hear anymore.
Sort of this with this, I have just to juxtapose this here, and this is what I get. And composition is given by push out. So if I want to compose this with this, I'm basically attaching this hypergraph and this hypergraph through the interface. not here that have to fuse. Since 1 and 2 are mapped into the same node here, while here are different, making the push out make them fuse here. So these two different here and up here. And the resulting hypergraph, and the resulting cospan of hypergraph is this one. So okay, with these two composition, I can easily transform every circuits into some hypergraph. This is the sequential, and I mean here we use the composition by push out and by disjoint union. And the way we do this is rather straightforward. And I think it appeared for the first time in this paper by Fabio Garducci, Raiko Ekel, and Marcela Bressa, because the bicategorical axiomatization of concurrent graph transformation. And we also exploit it in this leaks paper. It's rather obvious what it does, and you can see here a simple example. I mean, I think the translation from string diagram to cospan of hypergraph is rather straightforward, but here you can just translate. I mean, to this is just equal to the composition of the hypergraph denoting these two pieces, which are this, and this. And then if one does the push out, what one obtains is really just this 1 and 2. Okay, and an interesting fact is that there is a nice theorem already in the paper of Raiko and Fabio and Mercé, but also it's reproved in here, that for all possible circuits, they denote the same hypergraph if and only if they are equated by these axioms. If and only if they can be proved equal by mean of this axiom. Okay, now what about the inequality? What are these inequalities telling us? Well, it's rather easy to see that this inequality exactly correspond to homomorphism of hypergraph, of cospan of hypergraph. So what is an homomorphism of cospan of hypergraph? So an homomorphism is alpha, which go from the cospan ngm to the cospan nhm. I mean, here the interface has to be the same. Here we are considering to cell. It's just an homomorphism of hypergraph alpha, which commute properly with the interface, as we were requiring at the very beginning for the Chandra Merlin result. So it's quite easy to see that this can be proved by induction on the axiom, on the inequalities, that if C is smaller than D, then there exists an homomorphism from the encoding of D to the encoding of C. So the homomorphism go on the other way around. So let's see, for instance, if I encode this into an hypergraph, into a cospan of hypergraph, I obtain this. And if I encode this, I obtain this. And clearly I have an homomorphism, which map is in here, the two hyperedge in the only one, and this. So I show you this because this is one of the axioms, but we can also consider this. So this is mapped into the so this is the hypergraph with the empty interface, but which contain one nodes, and this is the hypergraph with no interface and which is empty itself. So it's really like 0, the empty hypergraph. And we said this is there exists X true and this is just true, and clearly we have an homomorphism from here to here. Okay, now it comes a bit of the technicality. I don't know why there is this strange green here. I realize only now. Anyway, can you hear me?
Yeah, yeah.
Okay. So I just want to say that this can be strengthened into an if and only if. Actually, we have that there exists an homomorphism. If there exists an homomorphism, then we also have the inclusion. And actually, I can state this in a much more precise way by formulating this as an isomorphism of Cartesian bicategories, but have to be a bit careful about the ordering, because the ordering is not really an ordering, but is actually a preorder. Let me explain. So we enrich the symmetric monoidal category of discrete cospan of hypergraph with the preorder given by as follows. So ng, the cospan ngm is smaller or equal than nhm if and only if there exists to cell an homomorphism of cospan from H to G. So in the other way around. And note, however, that this is not a genuine. This is not a partial order, but is rather a preorder, because one can have, for instance, that alpha make this diagram commute, and also beta make this diagram commute. So we have two morphisms in the two directions, but G and H are not isomorphic. So we call this category in this way, so with the cospan of hypergraph over sigma. Okay, and when we do this, we have also to redefine a bit a Cartesian bicategory, but it's really simple. We just remove posets and we write here preorder. And here too we say preordered Cartesian bicategory. Okay, all the rest is the same. And okay, so now this category that we have just defined is a preordered Cartesian bicategory, and we can also construct the free preordered Cartesian bicategory generated by some monoidal signature sigma, and this is exactly the same as the CB sigma that I introduced before. So the one of the graphical conjunctive query. But when we define the equivalence, we only use the first equivalence axiom and not those which involve the inclusion. So we avoid to use this and antisymmetry. We only use the axioms of a special Frobenius bimonoid. And okay, there is this theorem, which I'm not going to show, that say that the encoding that I've shown you, but which is kind of known since some time, of the free preordered Cartesian bicategory into cospan is actually an isomorphism of Cartesian bicategory. Okay, this is basically theorem 2. This is not. I'm not going to show you this. I want to quickly now prove theorem 1, where we use all the technology that we have seen so far. And the very first, the very first things to do is to kind of give a preordered version of theorem 1. So theorem 1 state that C is included in B if and only if for all possible model, it tells that evaluating C in the model is included into D. Note that model are morphism of Cartesian bicategory. Now the idea is that we want to make a preordered version, so we replace rel by span over set, and this is defined in the same way as cospan, but we now consider span, and then the inclusion here. So we have that A is smaller than B if we actually have a morphism from A to B. So it's the other order with respect to cospan. And for sure, composition is by pullback, and the monoidal product is by Cartesian product. So span set and rel are really similar, and actually one can see that if I quotient span set by the existing of mutual morphism, so basically by the antisymmetry of the preorder, what I obtain is exactly rel. And then from this observation, I can easily prove the theorem 1. Once I've proved theorem 1 for in the preordered version, so for span set. So I consider model into span set. And this is the most striking observation, is that actually if I look at model, so morphism from CB sigma to span set, what I obtain are actually hypergraph themselves. So why is like this? Because a model here is again a set, the set where I map 1. And again, n will be mapped into v up to the n. And then for every relational symbol in the signature, let me call this R. And then for every relational symbol in the signature, which go from with arity n and quality m, I need to assign a span from Vn to Vm. So what is such a span? Is basically a set ER and two function. And what is this doing? Well, it's the set of all hyperedge labeled by R. And here I have source and target function. So for each hyperedge, I assign n vertex and nodes as a source, and m nodes and vertex as targets. So a model in span set is an hypergraph, are exactly the same things. And I think this is interesting. I never saw this. I mean, we see hypergraph as per sheaf. We know lots of different way of understanding hypergraph. I never saw this in this way. So it also holds that every hypergraph is a model. I mean, it's obvious from this way of looking things. And now, because of the theorem 2, we have this isomorphism between CV sigma and cospan. Now we have that every hypergraph, since every hypergraph is a model, and the model go from CV sigma to span set. So, and since CV sigma is isomorphic to this, every hypergraph give rise to a morphism, which I call it U of G, which go from cospan of finite hypergraph to span set. And this is called the universal model given by the hypergraph G. And what does this universal model do? So basically it takes a cospan here and maps it into a span of set. And Dada, this is just the how to say, a span version of the omset functor. So for every, so if I apply to the hypergraph G prime, so to the cospan n G prime m, so this obtain what I get is this span. How does this work? It's basically saying take any morphism from G prime to G here and just precompose it with this with I, so you get a morphism in here, morphism like this, and precompose it with omega, and you get a morphism here. And then the proof of preordered theorem 1 followed by a simple kind of Yoneda argument. So this is the complete the preordered completeness. So I say let's we say that G and G prime are two arrows in are two cospan. And now I assume that for all morphism M, it holds that M applied to this is included into M. I mean, is smaller than this. I mean, these are span by definition, right? So then the inclusion holds as cospan. And okay, if this inequality holds for all possible model, for all possible morphism, it holds in particular for UDG. So I can translate, I can apply UDG to this, and what I get is hypergraph from G to, I mean, morphism of hypergraph from G to G. So what I get is this. And then I can apply U of G to this cospan, and here I get morphism from G prime to G. Now I guess you can see that in here I always have the identity of G. So I can apply alpha to the identity of G, and what I obtain is a morphism from G prime to G. And well, since this commute, if I precompose this with iota prime, precompose this with iota prime, I obtain exactly id composed with iota, so this is just iota. And similarly for the other leg of the cospan on. So this commute and this holds.
Sorry, Filippo, you're going very quiet if you sort of turn to the side like that. Maybe you have to put the volume up a bit.
Okay. I just said that I have that. So let me repeat the argument. So this, if this holds for all model, it holds also for the universal one. So I apply this inequality to the universal one. So I got this and this. The fact that the inequality holds here as span means that I have an arrow from here to here. And now I call this arrow alpha, and this alpha makes commute these two spans of set. And then I can pick here the identity over G, and the alpha will give me an homomorphism from G prime to G. And this homomorphism is by the commutation of this diagram makes me also commute this diagram. Therefore, I have built an homomorphism of cospan from G prime to G, which means that G, the cospan with G, is smaller than the cospan with G prime, which is exactly what we wanted to prove. And that's all. This finished the proof and basically finished the talk. I think I'm already a bit too late, and I hope you can have understood something. I realize only now that maybe I went too much into details. I don't know. I mean, I hope the community of graph transformation is quite close to these things, but not sure.
Okay, thank you very much. I mean, it's a bit over time, but not too much. So don't worry. We also started a couple of minutes late, I think. Right. Yeah. Excellent. So while, I mean, obviously people can ask questions in the chat if they like. Yeah, I had a question about the relation with rewriting, as you may imagine. So, so we understand if you put up your loft triangle again. I like that. We understand what rewriting is in some of these. In some of these domains. So obviously on the combinatorial side, so hypergraph rewriting. So that's clear, I think, and we understand I guess, through the paper with Fabio what the categorical version on the bicategories is.
Yes.
So it's not exactly. I mean, obviously, in that case, the bicategories, the bicategorical structure isn't just the ordering, but the rewriting structure as well, isn't it? So it's a slightly a different bicategory than the one you mentioned. So, but fundamentally, we know what rewriting means in that context. I would argue, and string diagram rewriting maybe is another sort of more generic example of that. But so what would happen in the on that other side, the logical? Is that obvious? And first of all, is that true what I just claimed? I mean, do you agree with that? Would that triangle hold up if you consider the sort of the natural notions of rewriting in each of those corners?
So this kind of question I've been really thinking seriously in the last years, and the point, I mean, the main difference that I see here is that now somehow also morphism comes into play, and when one considers logic and the categorical structure, one need also to consider the two structure, and so it's not anymore really the ordinary DPO. While when we only consider separable Frobenius bimonoids, we are really doing a double push-out rewriting. In here, we need something more, because we have somehow to quotient also with respect to this relation, which tell us that amorphism exists. So
is this a question of rewriting up to isomorphism, or concretely?
Is a question not up to isomorphism, up to the existence of two basically you want to equate any two graph for which there exist these things, and they call this, I think this relation is called the core of an hypergraph. So basically you want to say that core of G is equal to the core of H. So it's more like you want to rewrite cores more than.
So it's essentially logical equivalence.
Yes.
If you translate that into the logical side.
Yes.
Which is obviously more than isomorphism. Yeah.
Yes.
Okay.
Let me add that Jens Sieber developed a bit of this sort of rewriting theory. It was mostly used to somehow you can see any. So basically the idea is that okay, once we have these just for logic, we have model, and we can now start to think about theories. So rather than considering theories like groups, monoids, and so on, one can consider relational theory, which are not defined just by equivalence, but also by existential quantifier and so on. And for this kind of theories, basically, so you want to say, I don't know, I want to define all the transitive. I mean, I want to take the theory of transitive relation. So what you have to say, you have to impose that this is smaller than. Wait a second. I can put this. Yes, basically you have to say like this. Okay, right, and for sure this becomes then rewriting step, and then we have some sort of algorithm. I mean, I say some sort because it doesn't always terminate, but which is based on graph rewriting substantially. Yeah.
Okay. I mean, okay, so that's interesting. So basically what you're saying is we're looking for a notion of rewriting that is kind of more semantical, essentially. Isn't it?
Sorry?
So the notion of rewriting that is more semantical in a sense that you're rewriting equivalence classes of formulas or equivalence classes of graphs that have the same semantics according to some to a semantic mapping here or to a notion of model that you provide.
Yes, yes.
Which is obviously an interesting, yeah, it's a different perspective, obviously. It's not, usually we just look at these things structurally and also tactically. Okay, thank you. Barbara had a question. Barbara, you want to ask that yourself?
Yes, I can ask it. So thanks, Filippo, for the very nice talk. I got a tiny bit lost in the proof at the very end, but otherwise I thought it was very clear. Okay. I really like what happens in this setting that graph homomorphisms coincide with logical implication. This is probably also true because the logic is a fairly simple logic. I mean, there's only conjunction and existential quantification and so on. Are you aware of maybe a bit more expressive logic where you can do similar things, or is it this logic where things work, and if you extend the logic, you're kind of out, you cannot do much?
I mean, this logic is really what comes from the free Cartesian from the law of Cartesian bicategories, and it's really what we have somehow with also with hypergraph with interface. So if we want to extend, it's not that hard. For instance, if you want to obtain all the first order logic, is enough to add negation, which I know is messy, but if you add negation, you have all first order logic, but then things get a bit more complicated, and the logic is similar to these which are called existential graph by Peirce. So this is another line of work, and Pavel have been recently thinking about this. And say I didn't really thought too much about extending. But this is for sure a meaningful way of extending and of going beyond the regular logic. Yeah. Thank you very much for the question.
Can I maybe just add one thing, Filippo? I think maybe one reason why Barbara might be confused is because you started off talking about rel, but the theorem that you proved at the end was for span set. So how do we, maybe you could say a little bit about how to get from span set back to rel?
So basically the idea is that one has to, so I proved the theorem for span set, but then so the main observation, then there are a few technical bits, but the main observation is this one. I mean, if you quotient span set by antisymmetry, you obtain exactly rel, in the sense that now you take the existence of this as an ordering and the opposite as well. If you have these two and you quotient, you obtain exactly that. And yes, once you have this you get completeness for once you observe this, you get completeness for I mean, you can think, rel, you can see this as a jointly monic.
Yeah, that part was basically okay for me. Okay. It was fun. But thanks.
Okay, thank you.
Heiko, I think Nicholas has a question. I'm not sure whether you see him.
No, I cannot.
Thanks. Yes. So I just thanks a lot for the talk. Very, very interesting. And I mean, every time I see this, because I mean, I've heard of you guys working on this for a while. I'm always wondering, because essentially you are saying in this love triangle that in the end of the day, hypergraphs present particular models, as you explained to us, and then rewriting steps. I think that you have this work where you say a DPO rewrite step in this particular semantics of cospans with, I mean, for the contact points, a rewriting step, one of such is a sort of a witness of that you have an implication, if I understand correctly. Is that roughly how it works? You say like, a morphism is a particular proof of inclusion of the models, yes, of the semantics. So then, of course, then I mean, playing with it, then so essentially a rewrite step. Then, because of course we can, so what is a partial morphism then? Because I mean, then I could ask, can I produce myself a morphism through a rewrite step? I mean, if I were to do DPO rewriting in the semantics, and I looked at maps which have the identity for the left leg of the span, I would precisely produce myself a class of morphisms by rewrite, by push out essentially. So essentially, if I have one morphism and I take a smaller morphism over it such that I can form a push out square, I've essentially summarized a set of possible implications, yes? I'm trying to see, this is really not much with rewriting so far, but you said you could do DPO rewriting in the setting, yes?
Maybe I should be more clear on this. I think it's.
So you're saying you have a model maps to a hypergraph. You have sort of inclusion of the semantics of the models maps to a morphism in the hypergraph model. Is that correct? And in this hypergraph encoding.
Sorry, Nicholas, I lost the last question.
Sorry, you were saying you showed us how a model gives rise to a hypergraph in one side of the love triangle. Yes. Yes. Then a morphism of hypergraphs essentially is a witness of having some inclusion of the semantics. Yes. So if I were thinking like a graph writing person, then I would maybe produce myself such morphisms from rewriting steps, because it's a special case of DPO rewriting where simply the left, the input side is an identity. I mean, the span I use for the rule, I have a left leg, which is identity, and a right leg, which is something. So it seems then, basically, if the morphism I'm looking at is coming from a push out, I could see this as a rewriting step where basically the opposite, like in the push out, is then a smaller, in quotation marks, morphism between smaller hypergraphs that summarizes this, by taking this push out, I would essentially give me a witness of this larger morphism. So I'm wondering, is it the case that by looking at rewriting steps in this particular hypergraph semantics, I'm starting to see ways of proving whole classes of implications? I'm just trying to see the benefit of coding this as a hypergraph. Because I guess you're showing us that if you have a partial observation and this works anywhere in the hypergraph, you might as well summarize it as a rewriting step.
For instance, no, what you're saying, I found what you're saying is really interesting. It seems to me somehow also close to what I was mentioning, this algorithm that Jens is doing in his thesis. So if you have some sort of L smaller or equal than R,
exactly,
and
now you look at something. I think you have a notion of embedding. Yes, you can say now look. Yeah.
Then now you can say L is equal to L intersection with R. Mm-hmm. we can encode these two properly, and then so basically in the rewriting step you only do push outs. You don't do you don't really do. So what is L intersection? So let's say if you have a graph which represent L, and
I mean, I can't visualize it. I'm only asking. I'm just wondering what means push out square. Essentially, this would somehow relate to span.
If I visualize, it's easier. And then this is R. So this is just what they are when you do the intersection. You just glue them to the interface. So basically, you have a rewriting rule which tell you L has to be rewritten L intersected with R, which is just add R whenever you have L.
Exactly.
that's the way it works. And yes, so it's just a push out.
Now I could ask, for example, find me the smallest rule set through iteration, create me the morphisms that are relevant to my whatever that calculus is.
Let me add one thing, that in Popo last year there was this very beautiful work about, they're called eGraph. So they're using hypergraph to represent equivalence classes of terms. And the way they reason is exactly like this, and it's basically, I think, the same underlying structure that we have here.
Interesting. And so, relatedly, so then again, the question: what's the partial morphism of hypergraph interpreted as in this particular setting?
I don't think it's interesting. I don't think it's interesting logically because and if you have two more, I don't know.
Okay.
But I don't think that as a logical meaning. I must say, yeah.
Interesting. Because that essentially, but even in the case where you have, let's say, a push out, and then you at the foot take another push out stuck to it, like a derivation sequence in this language, should be interesting to look at. Because then essentially you could start to analyze because in these algorithms, I understand, well, transforming string diagrams always has a price that you have to find a strategy. I mean, even if you're given all of these relations, you still need a strategy to.
It's much more convenient using hypergraph. Yes. Yeah. That's why you want to do everything with hypergraph. Yeah.
Very interesting. So maybe I pass back to Reiko. We could stop the official YouTube streaming and still keep on discussing, of course, but then maybe it would be nice to see everybody in the gallery. So maybe Reiko, you can still here. So we seem to have lost Reiko.
Sorry, I'm here. I was just saying thank you very much, and let's close the official part, and we continue the discussion between ourselves. Okay.
Just thanks also from my side, and everybody who should be watching on YouTube would like to join the sort of informal discussion. I posted the link on the YouTube channel, and we are just going to close stream right now. But